Podcast reaction. This is a podcast with This Week in ML show. A shout out to Sam Harrington and his show, really very useful. The way he does it, also his guests are great. His questions are to the point. Just an example of, I think, what modern journalism means, which is, this is an expert. Sam Harrington is a domain expert that is doing journalistic work. I think as a former journalist, I really appreciate this type of work. And when people say, "Oh, journalism is dead and there's no use for it," and blah blah blah, there is tremendous amount of use and need for journalism. It's just not the kind of journalism that I was trained in, which was back in the day when I started. You were a generalist, just writing about stuff, and this just doesn't cut it anymore. I think GPT can do better than that, than a human. But what GPT cannot do is exactly what Sam Harrington is doing. Now, what is Sam really doing? I think he's doing two things. One is he's picking the right guests, and he's asking the right questions. So in this case, I'm going to discuss, he got Eric Nguyen on his podcast, Stanford PhD, working on the crossroads of DNA sequencing and AI. And the goal really here is, in a nutshell, is to build a foundation model for DNA and to, in my opinion, create the machine for Biotech 2.0. Biotech initially started with the ability to use organisms to create, let's say, insulin, right? That was the first one. That was how Genentech started. And the idea was we use biology to create medicine, for example, or, obviously things have changed way further down the road. So now we have CRISPR, let's say Cas9 and things like that, where we can use biology to create organisms that maybe can help cure disease, or we can actually even program cells through DNA editing to help themselves. So this is roughly the idea. And this is all, I would say, Biotech 1.0, or okay, if you want, you can say Biotech 2.0 could be sort of the programming of specific cells to do certain things. Now, this 3.0, if you will, is the next level. And what's happening here is we want to be able to, in virtu, design an organism that does certain things. And the inspiration comes from, like everything else these days, from large language models. DNA is a language. Its alphabet is the nucleotides. We tokenize it. We train it on large pools of data, and then we find a way to maybe prompt, actually, or in context learning and prompting, and we use all the techniques that we have in large language models to hopefully find a solution to a problem. Let's say, give me a DNA sequence that produces a protein that does X. Next level, give me a DNA sequence that solves Y, sickle cell disease. And lastly, I have sickle cell disease. What's the solution? The solution could be you need to program certain cells in your body to do this way versus that way, or you can design an organism, a drug, if you will, that you can take that solves the problem. Now, we're very far away from that, and certainly I'm not propagating for any hardcore like experiments here, because the risks are huge. But this is the beginning. This is the beginning, and that's why this is so exciting. So I'm going to discuss more technically now what's going on here. It's really early days, so I don't want to jump the gun. But I think this let's call it Bio 3.0. This is really very exciting. This is not an own podcast. It's Jan 26, 2024. This is Krim Delco. For the day, the fund is up 2.5%. The market is up 0.5%. For the year, we're up 0.5%. The market is up 15%. We're underperforming by 14.5%. Just before I go there, Uh, this is the first time in the year that we're actually up, which is great. There was some news in the electric car space. Volkswagen is teaming up with Rivian on the software side. I think this is worth its own episode. Our comments right now for this is one. I mean, this is obviously a testament for how critical the situation must be at Volkswagen in terms of software. Our opinion of Rivian is, let's say, mixed. We have real big questions about this company. So for Volkswagen to team up with them on software is, in many dimensions, I would say, a very weak sign, and just shows how far Tesla is ahead. This is all I want to say for now. I think it's worth doing a more in-depth analysis. I read the press release though, and it's very convoluted. There's no real information there, which is not untypical for Volkswagen, but it also signals that this looks more like some sort of face-saving exercise. Maybe it seems to me that the OEMs or generally large companies have an incentive to keep Rivian alive for whatever reasons. I mean, for them being some sort of competitor to Tesla, I think at this point, even Rivian doesn't believe that. But for some reason, people, whether it's Amazon or now Volkswagen, they why not just let them go bankrupt, buy the assets, whatever's left, and then build something real? Because you can't be wasting this kind of money on R&D and selling your cars at even below cost of goods sold. That's not a business. But anyway, this is certainly not the topic of this episode. What this episode is about is basically long sequence modeling. This is what we're talking about here. Eric's working on that. So what is long sequence modeling? I think in a nutshell, the difference between long sequence modeling and sort of vanilla modeling that we see in GPT and Claude and all these other models is that with long sequence modeling, we are looking at a very, very large set of tokens when we do prompting, right? And the reason that is a problem is that's both time and compute intensive. Given the mathematics of attention-based architectures, your sequence length, your prompt sequence length, raises the compute resources in a quadratic way. So what that means is that the longer you go, the much bigger everything becomes. The cost, the wall clock time. Wall clock time is the actual time it takes from input to output, which is different than things like flops per second or something like that. This podcast series is obviously not a technical engineering podcast, so I'm not gonna spend too much time. The links are in the show notes of the paper. But I think fundamentally what's interesting here is first the problem on its own. So we have a problem of long sequence modeling, and the solution is to use state space models, in this case convolutional neural nets, CNNs. And the advantage of convolutional neural nets is that they can be adapted to very long sequences without explosion of wall clock time and memory requirements. So this is roughly the outline of this whole project. This is Eric's PhD, and once you have the ability to do long sequence modeling, you can apply it to biology. Biology is a canonical example of the necessity of long sequence modeling because the sequence matters. This is key, right? There are situations in life when sequences are maybe not as important, and computer vision is actually one of them. Very often in computer vision, at least at first sight, sequence is not so important. If I look at the ocean, say an image of the ocean, it's not so important that on the left lower side of my image I have sand, and on the upper right I have a blue sky. Like, the context here is not so important. Plus, I can even predict that context. In other words, I can compress that image dramatically and not lose much information. That's not the case in DNA, because the lower left pixel, or the information here versus the information there, actually could matter a lot. The positioning of the token here versus the token there could be the information. And if I just overlook that, in other words, if I sort of compress that, if I say, well, I'm not just going to look at each nucleotide, okay, let's say one token, one nucleotide. This is what Eric actually has done in his paper. If I go per nucleotide, I have a situation where if I overlook one, if I compress, if I take shortcuts, I actually lose information. So I need to take the whole sequence in and then do predictions based on that. Now, the end goal, there's 3 papers that are discussed in the podcast. One is how it's using Fourier transforms for convolutional neural nets. That's a technical paper that talks about the actual engineering of convolutional neural nets to make them more adaptable for long sequences. And that has to do with the fact that if you go from attention to a convolution, in convolution you can use Fourier transform. You go from spatial information or into frequency, and then you can have a reduction in actually time spent of compute, because it goes from quadratic to linear. I think I want to stop there as far as technicality is concerned, because I'm not super familiar myself with all these concepts. But just think about it this way: you can use signal processing methodology to solve certain machine learning problems. And what I find interesting here, and this goes back to Chris Ray's keynote at NeurIPS last year in New Orleans, that in essence, we're talking about signal processing here. So what machine learning is signal processing. Just have different names. Signal processing comes from the telco area, when we were sending signals to each other, and now we're analyzing data. Data and signal is the same thing, right? We're looking for signal. We're looking for signal to noise. All the same problem. So that's just sort of as a side note. And for people who are thinking of studying electrical engineering, and they think, oh, I should be studying AI, I shouldn't be studying electrical engineering, don't worry about it. A lot of the electrical engineering know-how actually is transferable to AI. In other words, AI is electrical engineering. It just has different names. So we're using these electrical engineering methods from signal processing to lower the wall clock time, and also using flash attention, which is kernel fusion, to reduce the memory requirements. What kernel fusion just means is that we hope we can somehow reduce the convolution to a level that we can then run on a GPU with high bandwidth memory on a GPU. So again, those are technical problems that are addressed in the Fourier transform paper. I want to jump to the next paper, which is the HyenaDNA. Now that's the first application here, where they say, okay, look, we take the human DNA and we just do some simple tasks. We train it on human DNA, and now we want to see if we can do some sort of keyword search. Is the model smart enough to remember where stuff is? And the answer is yes. And then the next level, this is EVO, where they take microbial DNA, which is, by the way, available, and it goes back to what is the scientist of tomorrow. The scientist of tomorrow builds the machine that creates the solution. In order to build the machine that creates the solution, she needs to have access to data. Well, microbial DNA is very, very abundant. So we have, available, and this goes back to, we have actually lots of data. So we have an internet of DNA data. This, just as a tangent, I think a lot of fields in the next few years that will see massive um, advances are the kinds of fields where we've built big data sets. So text is one. We've built a big data set called the internet, and books, everything was digitized, so we were able to take advantage of that. FSD is one because Tesla's built an internet of driving data, and I think DNA is also one. So I'm very, very excited about this. I have my doubts about application in healthcare that has to do with corruption in healthcare and the difficulty of actually making money in healthcare and all those sort of things. Um, but that's different. That's an institutional problem. That's also us as investors not interested in DNA type investments because the problem. This is for another podcast. Excuse me for digressing here. But as exciting as Eric's work is, as exciting as Bio 3.0 is, we still have a lot of doubts about actually making money with all this stuff, and that's just because the institutional barriers in healthcare are just too big. But maybe this could be the breakthrough. We'll see. Anyway, so the beauty of EVO, and particularly large model EVO, is that they're going uh, from shorter context windows and smaller parameter size to larger and larger parameter size with larger and larger context windows. And they kind of, it's kind of like inverse ablation here, where you start small, you get bigger and bigger and bigger, and you see what's happening to your performance, what's happening to your, compute budget, what's happening to your time budget, and at the same time you look at performance, and everything is getting better and better. So to summarize, beautiful example, I think here this TwiML podcast episode with Eric Nguyen from Stanford about an application of foundation models in a different domain using the same ideas like in text, applying it to something new, which is biology, solving one of the biggest technical issues, which is long context window issues. By the way, they've been tackled also by Google Gemini, and they speak about this in the paper, and it seems like it's not clear how they tackled it. And before I finish here, I just want to also tie this now to vision, autonomous driving, and robotics. And the question is, do we need long context windows there? And the answer is probably not. Uh, but having them at our disposal, and this is something I have to think about a little bit more. Is there an application, a need, or maybe even an avenue of new ideas that can be tackled in robotics with long context windows? The answer at this point is I can't 100% see it. So if I saw it, I would say it. But it's just an interesting question, sort of as just keep it filed here for presentations and conferences in the future. What Eric does, he's using long context window technology to tackle problems in biology and to create, in my opinion, the foundations for Bio 3.0, which is foundation models for DNA, where we can prompt in virtu, we can prompt DNA sequences that generate chromatin sequences, which is, in other words, DNA that forms itself into a structure that then generates certain proteins, and the proteins are the workhorses of biology. In other words, we can go from DNA prompting all the way towards function, and then potentially solve problems like medical problems and all kinds of pharmaceutical problems with this type of technology. Thank you.